Katok, non-stationary normal coordinate along one-dimensional invariant manifold.
Hello. Okay. So first of all, I would like to thank the speaker and also thank the organizer for giving me this chance for delivering my talk. And I came here 35 years ago, as I counted. And okay, there was a big conference like this, and I was very happy to be here at that time. And okay, time passed very fast. Okay, 35 years later, I think everything's changed. Maybe the lectures are more, I think, have more varieties, and there are many, many new researches, and I'm very happy to see this. And on the other hand, I also very happy that this place is not changing. So it is, I think, almost the same as 35 years ago, and I found that very happy. Okay, and here I had get a chance to give a talk, and here I like to, okay, first I write a theorem. This is what I got recently, not very recent, but with Zhu and Zhan. And it says that, okay, maybe it's a bit small, but for C infinity answer flow in 3 dimensions, we proved that topological mixing implies exponential mixing for any equilibrium state. It's a kind of giving a dichotomy, because if it's not topological mixing, it is topological conjugate to suspension of Anosov diffeomorphism with constant root function. So it's a very specific case. Or if it starts to mix a little, then actually it's automatically exponential mixing. So, okay, I like this result. And here, actually, I don't speak about this result too much, but I want to focus on some technical problem behind this, the argument in the proof. And this is, okay, I can say that this is non-smoothness of stable or unstable foliation. And actually, I came to this problem long before, maybe 20 years ago, for 3-dimensional partially hyperbolic system. So I like to speak under this assumption. So we always assume that M is a 3-dimensional manifold, and F is partially hyperbolic, and maybe in order to avoid some complication by differentiability, maybe we assume that this is C infinity. Then we have splitting like this by definition, and each of these are 1 dimension, and usually not smooth. So this splitting itself is not smooth. Okay, and my task is how to analyze this non-smoothness of ES or EU or EC. Okay, and for this I like to start with non-stationary normal coordinate. Or normal form. So it already appears in the lecture by Federico. So, but let me just state the theorem. So, so this is, okay, the theorem tells that we can give a good parameterization of stable manifold of each point. Okay, for this is okay, smooth immersion. For each P, such that the first two conditions is not important, but we need to do it. So if you restrict it to, so this is somewhat not somewhat bounded. So if we restrict this parameterization to -1 to 1 or any compact interval, then it is smooth bounded, uniformly bounded, maybe with respect to P. Okay. And also we can show that okay, dependence on P is in some sense continuous. And second, okay, IP maps 0 to P, and then the differential induce map from the tangent space at 0 to this TP W U. Oh, sorry, maybe I like to discuss about unstable manifold. So we are at U, but we can do the same thing for S. And E. And this is isometric. So implicitly, we introduce some metric on M, but this is not important. But anyway, so I consider some Riemann metric on M, and then we suppose that this is isometric. And then this is the point of this theorem, that if you look things in this coordinate, actually the map F is linear. So write it, F P. Okay, this is R to R. And this is just a multiplication by constant from the UP times tau. And lambda UP should be plus or minus df P restricted to EU. Okay. So this is a theorem. And I don't know who this, maybe for me this is a kind of folklore, but maybe I can say that this is by Katok. But this kind of observation appears in many works. And okay, and not very surprising, but still it's interesting, because dynamical system choose one linear structure on each of these unstable manifolds. Okay. Okay, and now so this is the starting point of my observation. And then actually I'd like to, so as the title says, I'd like to extend it to extend this coordinate or log parameterization to some normal direction of this unstable manifold. So I don't know, this is good notation, but this is normal bundle. So maybe we may write n, but conormal bundle. So we consider elements of a cotangent bundle, and we assume that x, the base point, is in WP, and QC is normal to the tangent space of this. Okay, so this is just unstable direction of x. So in this theorem, we have a very good parameterization of WP. Now we like to look around it from this coordinate, so from this place. So of course there are many unstable manifolds. Okay. And we know that the holonomy is not smooth. But we may be able to say something, maybe in infinitesimal level, along this unstable manifold. And this is an observation that is in the core of this work. So let me just write as a theorem. So TZ. So there exists an extension of, so this is two-dimensional vector bundle over unstable manifold. So now, so space is, model space is this. So, and we consider this T star normal W. Okay. And so this is smooth trivialization. Of this vector bundle. And okay, then first we assume that I hat P is extend IP. So in the base we have just this map, and smooth, okay, bounded uniformly bounded. And then what we will see in this coordinate for the natural mapping induced by F, then it should be at least written in this form. So minus 1 df minus 1 star. So this is a push forward action on, and no, here FP, and this is I hat P. Then okay, for the then tau is a parameter on one dimension of this manifold, and then we consider two directions. Then what we will have is the lambda UP tau. Yeah, this is what we have. So this from this I hat P is an extension, so this is obvious. And then lambda SP inverse X and sorry, plus tau y and lambda c y. Not maybe -1. Where P is contained in the polynomial of order smaller than R, and R is decided by this lambda C P over lambda S and lambda U P minus R. 1 for maybe NEP. Okay. So if you choose, okay, this is decided by some condition or expansion or contraction of dynamical system, and so this R is decided by this. And if you choose R sufficiently large, then we can find some chart or local trivialization in which the dynamics, okay, of course, around this unstable manifold is, okay, take this normal form. Okay, and maybe I like to give some proof, because the proof of not too difficult. But maybe we just, I like just to finish what I like to talk, and then, okay, go back to the proof. Okay. Yes?
Can I ask, so you have X and Y?
Yeah. Yes, maybe okay. EC, actually EU plus EC. This is smooth along WP. This is the first observation we have to make. And then, of course, its dual space or normal space is smooth. And this is one direction. And this is maybe here, y-axis, x-axis is in this direction. Okay, another question? Yes? Excuse me? Z or? This? Tau. Oh, okay, I like to write tau, but sorry. But anyway, this is.
What letter is that?
Sorry? This is tau. Sorry. I don't know why. It's okay. So. Yeah, polynomial of tau. So. Yeah. So this is p tau, and this is a polynomial of tau. So along the parameter. So yeah, every fiber we have linear map, but the linear map changes with respect to this tau. Okay. And for other constants, for instance, lambda up, this is just depend on p, so does not depend on tau. So maybe if you this map is just okay, you have expansion by lambda u, and then you have some twist. Okay. And one remark is that this kind of chord trivialization is unique. Unique up to isomorphism. Like tau x, y to alpha tau beta x and plus p tau y and gamma y. Okay, maybe. Okay, this is one thing. And the other remark is that, okay, this kind of local trivialization is, okay, not very visible in the beginning. And one reason, okay, but, okay, let me see how we can find this in geometric manner. So just motivation for this coordinate. So let us suppose that Pi belongs to stable manifold of P. So, okay, but here you have this, and here you consider some piece of stable manifold. So this is unstable manifold. Okay, and you like to that we take a point Pi, and suppose that which approaches to our point P. Okay. Then for each point Pi, you have an unstable manifold, and it approaches to this our unstable manifold. And we want to consider how it comes. So we want to observe how it looks. So maybe you can put some observatory for each point of this and look at how they come closed. And so we take, so phi I, this is -1 to 1, R, so that I had E tau I tau is normal to this is not a very precise dash minus IP tau. So for each point, this is IP tau. Maybe you look, maybe take a closest point and consider this vector. So, okay, you are here and observe the nearby point in the unstable manifold of this WPI. Okay. So you look for the direction, and then maybe since we are considering cotangent space, so maybe you consider that the normal form. Okay. So this is the direction of nearby unstable manifold. And then what we can show is that if this phi I converges to some continuous function, then this belongs to polynomial of order R, or order smaller than R. And a little subtle point is that if you consider these things in reality, actually, in most of the case, it will diverge. Because, and that is the reason why we have a non-smoothness of unstable foliation. But, okay, sometimes we can choose this phi I and this point pi so that it converges, and then actually the limit will have a very good property. And when we consider this kind of problem, actually we like to consider non-integrability. So if this diverges, actually we have enough amount of non-integrability. So actually this is a good case. And so actually this local coordinate works when some exceptionally good or bad case happens. Okay. Now I want to discuss a little about this application of this coordinate, because okay, we have some good coordinate on this tangent space, and with this motivation, maybe it's good to consider this kind of object. So this is okay, what I like to call templates of stable direction along W P. Okay, and this is okay a set of functions such that, so this is from -1 to 1 to R, and so that IP at tau maybe this is psi p tau 1. This is normal to ES IP tau. So in this local, in this normal trivialization, we record the direction of ES. So now, up to this point, we always discuss about EU and unstable direction. But now we remember that we have another direction, okay, ES. So we just record it, and then we remember that actually we have some ambiguity or isomorphism in the local chart. So maybe it's natural to consider the quotient space. Okay, and so I like to call it template. And why? Because this contains basically all the information that about the non-smoothness or smoothness of ES along EU. And what is good is that, for instance, if you like to consider some behavior of stable and unstable foliation in microscopic case, right? So this is actually happens when we consider this kind of exponential mixing problem. And we want to see the non-integrability of stable and unstable foliation is something uniform with respect to, of course, point and scale. And then what we will see in this very, very small microscopic case, well, okay, if you consider things along unstable manifold, okay, W, but it is very, very small. But okay, then we pull back, okay? Push forward, okay? Since it is unstable direction, okay, at some point, it comes to a unit scale. Okay, then we observe this, one of this as an ES, direction of ES. Then, okay, we just push forward. Then we will see what is happening in this microscale. And we can do this for stable direction also. So in some sense, if you see uniform non-smoothness for this, then actually you get uniform non-integrability, and where uniformity is about the point and also the scale. Okay. And then let me observe that tau s Ts is compact because it depends on the P continuously, maybe at least in C0, maybe in Helder, I think. So it's an image of P is on the compact manifold, so its image is compact. And this is Helder, so finite Hausdorff dimension, right? Because actually this P to phi P is Helder. So actually this is somewhat small subset in infinite dimensional space. And also tau s has some non-self similar property. Let me use this picture. So if you have a point P and the unstable manifold of length, okay, unit length, and then, okay, we know some information of stable direction along this, inside this, okay, maybe phi P represent that information. Then, okay, if you cut small piece, then, okay, expand it by flow. Okay, then so that it becomes a unit size. Okay, then you get another element of here, right? Maybe this is Q, so another point, okay. And especially if one unstable foliation is minimal, then actually if you give a one element element over here, then actually you can get information of this for almost dense point of this, because okay, unstable. This push forward will dense. Then taking limit, but actually this is compact. So basically, if you give a 1 point and give some extra information, then you reconstruct this space again. And one of the important consequences of this is that I think this is at some point Ziwan found is that theorem is that if tau s, so temperate, contains 0 or some of this function is just a polynomial of order smaller than r, then actually it is always in polynomial. Because if in one point you have polynomial, then if you push forward, it's by f in small pieces. But still, okay, since we have this theorem, actually the image is also polynomial. So in this space, so almost all point we have that this is contained in this. But then by continuity, actually, we have this. So this implies that, okay, some dichotomy that Ts is just one point in this quotient space, or it is separated, because this is a compact set, so this is separated from space of polynomial. And this is a very good observation, discovery, because, okay, yeah, and if it is separated, then we can show that we have exponential mixing. Okay. Now I don't know how much time I have, 10 minutes or? I don't know, maybe 10 minutes or, yeah, okay. Then let me, excuse me? 12 minutes. So let me try to prove it. Or if there are any question, maybe you can. Okay, let us prove it. But okay, I did one first important point is this one. So okay, thank you for the question. And other thing is, okay, and this is of course invariant. So this is one thing, or A. And B is, actually this is a classical thing by Anosov, maybe, is that if you take a wedge product of this, so T star W, T, so this is a vector band we are considering. Now we take a wedge product. Okay, this is 2 dimensions, so basically. So this is a kind of volume element along unstable direction. Then admit non-vanishing section that is invariant with respect to f, of course, up to constant multiple. Application. Do you agree? Because if you look into the proof of the Anosov theorem about the absolute continuity of unstable foliation, it appears basically if you consider two volume element along unstable, foliation manifold, then actually you can consider some parallel transform of a volume element. Of course, the shape is maybe become much more complicated, but if you consider just infinitesimal volume element, actually you can just transform it. And so this gives an invariant section. And this is, invariant in the sense that if you map here, then, F, then you get another one. And this relation is not, this is not, this section may not be mapped to another, but up to constant it's same. So with these two observations, you have a good restriction for the form. So I may say that so let me say that we can replace, suppose that this is, we don't claim that this is polynomial, but just C infinity. Then actually these two proves this, right? Sorry, maybe I also have to say that this one-dimensional bundles admits a similar non-vanishing section. But this is also, the proof is quite similar. So we have this. So finally, suppose that we have such an intermediate type of trivialization, then how we can observe in the transition given by F. So suppose that we have some section tau, phi tau 1. Then in this local chart, we will, as it is F, maybe it's tau. Then if you push forward, what we will see is this lambda s inverse phi tau plus something psi tau. This is C infinity. Plus here you have lambda C, lambda C inverse. Maybe I did this computation yesterday, so I think it's okay, but if you like, you can check it. And of course, we like to, so this is tau dash. And so, no, S dash tau dash equals this. Then of course, I'd like to normalize it. So what we will have is tau dash and lambda s inverse phi and lambda u. Okay, this tau dash is lambda u tau. So we minus 1 tau dash plus something. This is actually, this part is not important. And then 1. So the direction is transferred like lambda tau to, no, I did something wrong. No, divided by lambda. Lambda c over lambda. Lambda s. So lambda s, lambda c, and phi, lambda u minus 1, tau dash, plus something. So actually this factor is bigger than 1. So we cannot expect this if you do this process for a long time. We cannot expect that this converges. But actually, you consider derivative of r times, okay, dr tau, phi tau. Then you get this factor for r times. So lambda s, lambda c, lambda u minus r, and phi something. And so this makes things convergent. So actually, what we can show is that this process will not converge. Maybe this is what I said in the remark. But if you consider this r's derivative, then it basically, if you go back and push forward things, then this part will converge exponentially. And then, okay, we have find some limit. And this, if you make this limit as an zero section, then you will get this coordinate. Okay, let me finish this part.